Yeah, so what I'll do is I don't know, try to make it accessible, possibly interesting to everyone in the room. So.
Okay, very good. So, welcome back, and Djordjo Milovic will talk about that title.
Yeah, cool. So in number theory, we're often interested in solving equations over Z. And a lot of times it's useful to view them over rings that are slightly larger, so number rings. So if you want to parameterize all Pythagorean triples and you look at this equation over the Gaussian integer, Gaussian integers, it works out pretty well. So if you want to show that the Fermat equation has no non-trivial solutions, you might view it over the cyclotomic integers. And this works out some of the time, but not always. And so one of the reasons that it doesn't work out always is that a number ring, unlike the integers, is not always a unique factorization domain. So this is one of these standard examples that probably many of you have seen. So 10 factors in 2 different ways into reducible is in z adjoint square root of minus 6. However, if you look at these factors and you look at the principal ideals generated by them, if you further factor these ideals, you see that these 2 factorizations are actually the same factorization on the level of ideals. So these number rings always have unique factorization into prime ideals. So so there are 2 main obstructions in passing from ideals to elements. One of these is that not every ideal is principal. Not every ideal is generated by one element. And so to measure the failure of this, we define the class group. So this class group will be trivial if and only if every ideal is principal. And so if and only if the number ring is a unique factorization domain. And so in the example that I showed you, the class group of this number ring is isomorphic to a group of 2 elements. And the other obstruction is that even if you have a principal ideal, it may have infinitely many generators. And so, for instance, if you join a square root of 2017 to Z, and you look at these 2 gigantic integers, then A plus B times the square root of 2017 divides 1. Okay? So if you multiply an element by any power of this integer here, of this algebraic integer, you'll get another generator for the same principal ideal. So the first 2 slides, I guess, were just to convince you that class groups and units are interesting objects to study. And so number theorists do a lot of study of these 2 objects. So let's get down to business. So let P be an odd prime and consider the quadratic ring z adjoint square root of minus 2p. So Gauss showed that the class group of this number ring, the 2 part of the class group of this number ring is cyclic. So in particular, the 2 part of the class group is completely determined by the highest power of 2 that divides the order of the class group. This is called the class number. So the 2 part, again, is determined by the highest power of 2 that divides the class number. And so what I'm interested in, what I work in, is, so the subject is vaguely called arithmetic statistics. So basically, one can look at there are many algebraic invariants in number theory that tell you something about the arithmetic of the underlying objects. And so what I'm interested in is to see how these invariants behave on average. So in this particular case, the invariant is the 2 part of the class group. And so we're interested within this family of fields, as you vary P over the odd primes, how does this exponent R behave? Okay, so we'll focus on the case that P is minus 1 mod 4, because the case that P is 1 mod 4 behaves differently. And so we're going to count primes up to x that are minus 1 mod 4, for which some power of 2, some specific power of 2 to the k divides the class number. And so if you do some numerics, you see a table like this. So you see half of the prime numbers, approximately half the prime numbers are minus 1 mod 4. Those primes for which 4 divides the class number occur about 1/4 of the time, for which A divides the class number about 1/8 of the time. So it's pretty clear from the evidence that the conjecture should look something like this. Okay, so the density of primes that are, the density of prime numbers that are minus 1 mod 4 and for which 2 to the k divides the class number should be 1 over 2 to the k. So what are some of the results in this direction? So already in the 1930s, Rede showed that the conjecture is true for k equals 2, so for divisibility by 4. In 1969, so with for 2, oh no, so we already restricted ourselves to the primes that are minus 1 mod 4. Yeah, so for all of those, 2 divides the class number. Yeah, that's okay. With a basic application of class field theory, Hasse in 1969 was able to prove the conjecture for divisibility by 8. And so since then, I mean, so, sorry? Rede, yes, in a sort of in a, I don't know, it's Hungarian, so I'm not sure. The next step would be to find out how often these class numbers are divisible by 16. And so there hasn't been much progress on that since then. So until I proved for my thesis that the conjecture for divisibility by 16. So you might ask, why is this interesting? Why do I care about divisibility by 16? So I guess one of the reasons is that I believe, to the best of my knowledge, this is the first density result for the 16 rank. So to detect how many elements of order 16 there are in any family of number fields, for class groups in any family of number fields. And so I'll tell you actually another reason this kind of result might be interesting. So what?
You will also tell us why there is no general result?
Yes, this will be clear from what I'm about to say, yes. So how are these results obtained? So Rede proved actually that divisibility by 4 is equivalent to the prime being minus 1 mod 8, and Hasse proved that divisibility by 8 is equivalent to p being congruent to minus 1 mod 16. And the significance of this is that these conditions can be expressed in terms of the splitting behavior of p in some extension that does not depend on p. So in these two cases, you look at the cyclotomic fields generated by the 8th and 16th primitive roots of unity, respectively. So to decide how often these cases occur, you can use the Chebotarev density theorem. So this tells you that the splitting behavior, so the density of primes that split in a certain way in a fixed extension of Q occurs with frequency that you would expect. Okay, so in particular, if you apply this theorem to the two cases above, you get the density is 1/4 and 1/8. Okay, so in the theorem above, this M is either the Q adjoint zeta 8 or Q adjoint zeta 16. So I'd like you to sort of vaguely remember what this error term looks like. So this here is the main term. This is the number of primes up to x. So this is some rational density.
Abby remembers it from Friday night.
Yes? Okay, good. Okay. Yeah. You'll never forget it? Okay. So, you have seen that the densities, you've seen the numerics. So those densities look like rational numbers. And the Chebotarev density theorem is something which gives you densities that are rational numbers. So Cohen and Lagarius in 1983 were led because of numerics and, I guess, general reasoning to believe that that in every case, there exists so if you look at a family of quadratic number fields of the form Q adjoint square root of d times p for some fixed d and p varying, there's going to be an extension, a normal extension of Q that depends only on d, so that the 2 to the k rank, basically how many elements of order 2 to the k there are, so the 2 to the k rank of this group, of the class group, depending on p, will be determined by the splitting behavior of p in this fixed extension. And if such a conjecture is true, this tells you by the Chebotarev density theorem that the density for the 16 rank, for instance, exists and is a rational number. And so one might be led to look for such a governing field for the 16 rank.
You mean it's the probability of getting that for Banks conjugate success?
Yes. Yeah. So sorry, the question is?
You say it's determined. You mean it's determined, it's equal to
Yeah. So
Probability of that.
yeah, exactly. So the 2 to the k rank is determined by the Frobenius conjugacy class. And so then the number of p for which the 2 to the k rank is equal to a particular integer has a density by the Chebotarev density theorem.
No,
Yes.
because of how it's determined. You're saying that the
Oh, yes, yeah. So it depends. So it's determined, for instance, so this would be the type of, so the theorem would say that if the Frobenius of P in this extension is equal to, a given conjugacy class, then the 2 to the k rank is constant in this conjugacy class. So it's a,
the order of that conjugacy class?
yeah, exactly. The density will equal to that, yeah, of course. Yeah. So, okay. So this type of field is called a governing field for the 2 to the k rank. And so Stefan Aachen proved in 1989 that governing fields exist for the 8 rank. So no matter what d you take and what, as long as, so no matter what d you take, if you look at this family of number fields, the 8 rank will be determined by the splitting behavior of p in some normal extension depending on d. However, no governing fields for the 16 rank have ever been found. So in my thesis, instead of finding a governing field for the 16 rank, what I did is I used another criterion. So if you write a prime number p as if you write it as u squared minus 2v squared, so we take a prime that's minus 1 mod 16 for which a divides the class number, where u and v are positive integers and u is 1 mod 16. It turns out that the divisibility by 16 is determined by the value of this Jacobi symbol. So this is like a quadratic residue symbol, so extended multiplicatively. So if p is minus 1 mod 16, you can look at this symbol, and if it's plus 1, then 16 does divide the class number. If it's minus 1, it doesn't. So in order to prove the conjecture for 16, one would have to show that these plus and minus 1s occur equally often, right? Because we know that for 1/8 of them, a divides the class number. If we want to show that for 1/16 of them, 16 divides the class number, we want to show that these plus 1s and minus 1s occur infinitely often. And so, yes?
In this game, you always try to run a criterion for exact divisibility or just divisibility?
No, so this is just divisibility, not exact divisibility. So to get exact divisibility for 16, one would have to know what happens for 32. Yeah. So, so the main result is that this symbol oscillates, okay, where u and v are chosen as I wrote in the previous slide. So the significance of this, I guess, is that so they not only oscillate, but there is a power-saving error term. So the number of primes up to x that are minus 1 mod 16 is a constant, so 1/8 times about x divided by log x. So this term here, sorry, where is it? This term here saves a power of x. So this is significantly smaller than x divided by log x. Okay. So the best known zero free regions for L functions are of this type. So you see the zero. So this is the line real part is equal to 1/2. This is real part of is equal to 1. And so the best known zero free regions are of this type, where the region tapers off and gets closer to real part equals 1 as the imaginary part goes to infinity. And these types of regions give you error estimates of this type, as the one in the Chebotarev density theorem. However, to get an error estimate of this type, where you save a power of x, you would need to have a zero free region that extends sort of uniformly to the left by step delta. Okay. So what this says is that if there were a governing field for the 16 rank, then my theorem would imply that a difference of prime counting functions of the Chebotarev type has an error estimate that is sort of that is much better than anything known today. That is sort of in the direction of the Riemann hypothesis. So the Riemann hypothesis is this with delta equals to 1/2. So this sort of gives a strong suggestion that there is no governing field, and that future sort of work on this will have to involve some new techniques. Yeah, so I don't know if I have 1 or 2 more minutes or not really. I can end here.
Not, but I can
Okay.
give you one for trying.
You can give me one. Okay. So it turns out, so I told you about a little bit about the class group. It turns out that one can look at this problem about units as well. And so if you want to look at for how many primes, odd primes p, this negative Pell equation is solvable. This is basically asking for how many primes p does the number ring z adjoint square root of 2p have a unit of norm -1. So this is closely related, the methods are closely related to what I described so far. So the conjecture is that the density of such primes p is 1/3, and the best known bounds are 5/16 and 3/8. And so to improve this upper bound a little bit, one would need to know for those primes that split completely in here, so basically for those primes for which the 8 rank is determined, to determine a criterion for a certain subextension of the Hilbert class field of this real quadratic field to be totally real. And I guess one approach to this could be to develop some sort of non-abelian class field theory over Q adjoint square root of 2. I mean, it would have to be very explicit. In a sense, it would have to be conducive to analytic number theory, which I don't really have time to explain right now. But if you're interested, then I can let you know more about it. OK, thank you for your attention.